the topics that you need to have at least a basic understanding of in order to appreciate some of the things that we deal with when we are looking at device drivers is this concept of virtual memory, right? Now, the first question is, why do we need virtual memory? And well, part of the reason, as I'll explain a little bit more, is that one of the reasons why we bring in this concept of virtual memory is we want different processes to be isolated from each other. Okay, so what do we mean by isolated from each other? As I've already said, one process should not be able to read or write the data corresponding to another process. This is especially important when we have multitasking. Otherwise, of course, there's no concept of multiple processes. And it has direct implications for the security of the system, right? Okay, so now if we assume that, the justification, the motivation for virtual memory is there, so what does virtual memory mean? It means that when somebody is actually using a pointer, it cannot be that someone else should not be able to guess what physical memory that pointer actually corresponds to. In other words, every pointer that I use should be given some kind of a fake name, so that if somebody else tries to guess, okay, this pointer actually corresponds to this location in memory, most likely they are going to be wrong, right? That is one. And the second is, of course, the operating system itself will block them from accessing things. So even if somebody manages to get the pointer that someone else was using, the operating system will say, wait a minute, you do not have access to this portion of memory. Now, this becomes tricky when you keep in mind that the memory, the actual physical memory where a program gets loaded, is known only at runtime, right? I don't know where exactly in the entire memory of my system my program is going to run until it actually starts running. So this memory addresses, the virtualization, has to be something that happens at runtime and not something that is, pre-compiled and sort of stored once and for all. So how do we do this? Right? Practically, the operating system provides a virtual memory space to every process, right? And this is a set of addresses that are different from other processes. Now, when I say different, the interesting thing here that you need to keep in mind is it is possible that two different processes might see the address, let's say 0, 1, 2, 3, 4, right? But that address 1, 2, 3, 4 corresponds to different physical memory locations for the two different processes, right? And that translation between the virtual address, which is what the process sees, versus the physical address, which is where it is actually stored, is handled by the operating system. Okay. So the OS kernel does a translation. It takes virtual addresses, which is what the process sees, to physical addresses, which is what is actually present in the hardware, and back, meaning that if I actually get data back from a physical address, I will need to convert it into an appropriate virtual address that the process can see. Okay. So an example of that is this picture that we have over here, right? The picture on the left shows what a individual process sees, right? So this is the process virtual address space, right? And I might find that the actual code corresponding to the process has been loaded in at this address, right? Some 400000. Okay. I also say that the data has been loaded into this address 600000. And the heap, which is basically where all the malloc and related memory allocations are going to happen, will start at this address 100, etc. There could be something else which is memory mapped, maybe for IO peripherals. And then this process will have a certain stack memory, right, which sort of usually goes downwards. And that is also where, for example, I create the temporary, every time there is a function call within this code, it creates something on the stack, right? And I have the stack pointer, which basically allows me to sort of go in a certain direction. Now, I might find that, in practice, I probably put the stack at high memory, the heap at low memory, and they sort of grow towards each other. There are various different conventions that are followed. So this picture is not necessarily representative of exactly how the memory is laid out for a given process. What is important is these numbers, right? Or rather, the numbers are not important, and that is the key thing to keep in mind. What the process thinks is address 4000 might actually correspond to some frame, right, a block of memory in the DRAM, which is an actual physical memory corresponding to, on whatever the motherboard of the laptop or desktop that you're working with. You might find that, let's say, the heap memory that according to this is at a location 0x100 is actually mapped into a separate frame of DRAM, which physically is closer to the first frame, right? Or rather is in between this frame 101 and the frame 450, which is where the data is stored. So the order in which I see things over here versus the order in which they are stored in memory could be completely different. This is the physical memory actually available to the system. It is seen only by the operating system, right? This translation, that this memory corresponding to this particular process should be seen in this frame of the DRAM, is data that is stored somewhere in the operating system. The operating system decides at runtime. It doesn't decide ahead of time. For each process that is starting up, it says, okay, I need to pick a chunk of physical memory and say, okay, this part of the text is mapped onto this physical memory. This part of the text code is mapped into this physical memory, and so on, right? So the operating system manages all these different memory blocks and does this kind of map. In between, I might also find that, my DRAM itself has been mapped in a certain way such that there is one range of addresses out here, another range of addresses somewhere out here. And in between that, I have an address which corresponds to the physical address of a device. Now, how do I access a device from a program? I need to use MMIO, right? And that essentially is what I'm calling the memory map region out here. Of course, that would most likely not be directly a process accessing it. It would be some kind of a device driver, right? Which takes care of, okay, how do I take this memory map, translate it into this physical address, and actually give the access to this by means of the appropriate driver interface. Okay. So, to summarize, each process sees its own virtual address space, and there are physical structures called page tables which help with the translation of virtual addresses to physical frames of the system, physical addresses basically. And the MMIO regions, they live in the physical address space. They are somewhere out here. But the individual applications don't know and they don't care. The only thing that knows where exactly the MMIO region is going to be the operating system. In particular, the driver code that we write in the operating system. And from there onwards, if I actually want to access that device, I'll have to go through a system call into the driver and then reach the actual peripheral. So the key part over here is because of the fact that each process sees its own virtual memory space, right, virtual address space, the pointer that I see in a C program has no direct connection with the physical address of the data that is stored. Okay. This is true when you're dealing with an operating system. Okay. When you're dealing with bare metal, a pointer that you use is directly corresponding to a physical location. In an operating system, it's not. It is virtualized. Where that really hits you is the fact that unlike the bare metal code that we showed earlier, where we directly had a reg32 macro, which just declared a pointer and dereferenced it in order to write data into a location, I can't do that anymore, right? So if I try writing into a specific address location out here, I don't know where in memory that's going to end up. In particular, it's almost certainly not going to go into the address corresponding to a device. So that is basically where a device driver has to come in. And this is the part that we need to solve if you're going to create a device driver. Now, how do we go about doing this? We are going to use a specific set of functions, right? The primary one being this thing called ioremap. Okay. So the flow is something like this. I have got a peripheral. Let's stick with our smart timer, right? So what does a smart timer peripheral look like? It has a certain set of addresses associated with it. Well, in this case, I've mentioned the 4 KB address space. The smart timer was less than that. We basically used, I think, 6 bits of address, right? So maybe just a 64 element address space, but it doesn't matter. You could use a larger address space. So 16 bits would have corresponded to 4 KB, right? Or 12 bits would have corresponded to 4 KB. And we could have a choice, right, of exactly how big this address space is. This is something that is decided by the hardware designer, right? The person who is actually building the module and packaging it as an AXI peripheral for use within the system. Now, the operating system knows this physical address. It needs to do something whereby it can, but even the kernel is not going to directly sort of access this. What the kernel does is it's also after all some kind of a process in there. It, rather than directly trying to access these memory locations using this pointer, it instead declares a new pointer base. And what it says is remap this particular address and this 4 KB address space, which is basically 12 bits out here, right, into this pointer location. Now, if I was to actually go in there and try to print out the value of what does this base look like as a hexadecimal value, it would most likely not look like this number. It would be something else. I don't know what number it would be. It would change from one run of the system to another. The point is, it doesn't matter. All that the kernel cares about is now it has a pointer which allows it to talk to this particular location. So why do all this rather than directly talking to this? Because at the end of the day, I need to sort of once again use specific system calls, right? Write-L and read-L. And by sort of capturing this pointer out here and using it, it allows me a certain degree of control, right, over how exactly I can communicate with these specific locations, right? Now, you might notice one extra thing out here. This, when I declared base as a pointer, I also use this __ iomap. This is an attribute which is specified as part of the C language, which basically says that this particular pointer needs to be declared as an IO type pointer. What makes that special? Regular pointers correspond to locations in memory. What that means is that because the memory might be slow, I might have a cache memory sitting in front of it, right? What does the cache do? It basically says, okay, if you have a slow memory like DRAM, I will use a fast cache memory sitting in front of that DRAM in order to hold the data if you are reading large amounts of data and then give it back to the CPU faster. Or if you try writing into that location, you first go into the cache and then get flushed out into main memory at some later point in time. Now for IO devices, I do not want that. I want them to get flushed out immediately. So by declaring this attribute as an IOman, it means that the pointer, anytime I read or write from that pointer, it will directly go and affect the value in the pointer. So you'll see that I also use these functions write-L and read-L rather than trying to just dereference the pointer. This is a cleaner way of allowing the kernel to basically do this mapping, right? And finally ending up writing into this location base plus control offset. So you give the value to be written and you give the address to write it to. And this write-L function will do this mapping between the virtual address and the physical address and write it into the correct location. Okay. Similarly, if I want to read, I use the function read-L, which essentially is like a pointer dereference, but manages to calculate the address, dereferences it, and gives me back data. All of this is happening in kernel space, right? And what we do is we wrap all of this into some set of functions which are provided as system calls. What are those system calls? In user space, I'll probably use a system call like open, read, write, or IO control, right? All of these are functions that any program, so over, read, write, open, and so on, are the direct file level manipulation functions that you can use. You can write a program using that, right? You cannot write a program directly involving iomap and write-L, read-L unless you are trying to compile something to run within the kernel. Okay, so that's something to sort of keep in mind over here. If you are writing any of this code, it will only compile in such a way that it has to be run as part of the kernel. You cannot run it like a regular program. This part, on the other hand, can be run as a regular program. And therefore, this is the difference where the kernel abstracts out the IO remapping part in order to give you a set of functions that you can use to communicate with the device. It exposes those through means of system calls. And user space can then use those system calls to then eventually talk to the peripheral. Okay. All right. So just to sort of recap this notion of addressing, right? We have virtual addresses which are in user space. They are per process, but they cannot see physical addresses. The kernel virtual address is the kernel's own virtual address space, right? The kernel also uses virtual addresses rather than physical addresses in order to sort of, the primary thing that is the reason why the kernel does not use physical addresses is at some point, even the functions that the kernel is using need to be mapped into certain locations in memory. And different libraries used by the OS might end up in different portions of the physical memory of the system. So you don't want to sort of fix and say once and for all that, this particular library, let's say the standard IO, the printf function, is always going to be at this particular physical location. I don't know. Depending on how the operating system loaded, printf might end up at one physical location or at another one. The kernel doesn't care. What it does is it finally says, I want a pointer, but rather than trying to find the physical address out there, it just uses its own virtual address space. And when it is trying to communicate with either the OS code or with a device, it undergoes one more mapping stage, right? Either using the memory maps or using ioremap in order to communicate with the physical addresses that underlie this. Okay. So the same abstraction which applies in user space is also used in kernel virtual address space. The physical address is the actual DRAM or device address which is used inside the SoC. We also have the sort of bus address space, right? Which is which of the physical address space locations actually correspond to registers. Because after all, I have 4 KB of address space. Not all of them actually correspond to physical registers. So there is a sort of small subset of that which is used by the actual bus. The rest of it will sort of return either a save error or some kind of invalid response. Okay. And you could also have some kind of a remapped address, right? Where if you have a memory management unit, you might find that the DMA module, the direct memory access, since that basically takes data directly from a device and transfers it into the memory of the system, the device also cannot know the physical addresses of other locations. What it does is, let's say that I'm transferring data from an Ethernet card through DMA into some physical location. The Ethernet card does not know the actual physical address corresponding to the final destination. It also sees a virtual address, right? So virtualization is used heavily throughout all the memory accesses. It is important for security and for sort of preventing various kinds of issues that can happen if you're not careful with it. And it is all handled by the operating system.